In this video, we'll be explaining how selection sort works and why it is in the order of n squared or quadratic time in complexity in the best, average, and worst cases. So before we get started, let's talk a little bit about what selection sort is. So it is a simple sorting algorithm that repeatedly selects the smallest or the largest, depending on the sorting order. But for this particular demonstration, we're looking at the smallest element. So it selects the smallest element from the unsorted part of the array and swaps it with the element at the beginning of the unsorted part. I'll be specifically showing what this line means by showing you an example of how this works. Okay, so I thought it's going to be different this time. I've already got the code because the algorithm for the sorting selection sort is pretty much out there on the internet. So I thought I didn't want to waste your time just spending time writing the code. I thought I'd rather save the time and use it to explain how it works instead. So I'm just going to show you what I've currently got. I've got a function here. Now this function is used to perform the selection sort on a vector. So we've got a vector, and this is a vector of integers. So you can see the data type is an integer. And here what we're doing is we're passing that vector by reference. Now, passing it by reference allows the function to directly operate on the original vector, which here we called array, ARR, and it's passed from the caller. So the caller is, say here, we passed the vector to it. And we come back here. The reason why we wanted to pass by reference is so that any changes made to the array within the function will affect the original vector. So that's the function for the selection sort, and we've explained why we're passing it in by reference. But I'll come in and expand this to explain how it exactly works. But before that, let's have a look at what the main method has. So initially for the main method, we've initialized a vector with some numbers, and I've chosen a smaller range of numbers because I didn't want to have a long list of numbers, making the video extremely long when we're trying to explain how this is going to be sorted. Again, I made a previous video on just right before this video on vectors. Have a look at that. But this is a vector of integers, and it's called numbers. We then looped using a for each looped through the original vector and displayed it right before it is sorted. We then printed out a new line, and then we called the function selection sort, passing to it the vector. This will, or should, if it worked correctly, sort out the the vector of numbers using ascending order. What we then did is displayed the array again using another for each loop to display the list of numbers, but now sorted. So let's run and see how this actually works. So what I want you to do is probably ignore this part. This is something I put in for debugging purposes. But initially what we want to look at is the vector before it was sorted and after the call to selection sort, and then after it's sorted, it's actually sorted in ascending order. If I added more numbers, this should still work correctly. So let's just say I added -1, 4, 99, 121, I don't know, -6 should still work. Let's compile and run it. Again, please ignore the middle part, but this is actually now sorting in ascending order from smallest to largest. So it's pretty much, it is working correctly. I didn't realize I've got two positive ones and one negative. All right, so I'll just undo and then let's have a look at exactly how this works. So now I'm going to expand the function that takes care of sorting the vector in ascending order. Now, the first thing we do is we want to get the size of the vector. So this is stored into a variable called n. So what that means is I'm just going to copy some comments that I've gotten prepared beforehand, again, to save you the pain of watching me type. So what we basically have, I'm just going to do it like this. So that's what the original vector looks like. 5291. I'm just going to double check. Yeah, 5291. So here means n is equal to 4. So basically, that would be 4. Let me get rid of that. Now, what I've got here is the index. So that's sitting at index 0, that's sitting at index 1, and that's sitting at index 2, and that's sitting at index 3. Now, let's look at this line by line. We want to iterate through the vector elements. So we want to loop through all elements except the last one, which we will take as already sorted. And I'll explain later why or how this is already sorted. But we have a loop that goes from 0 to n minus 1. Now, if n is equal to 4, 4 minus 1 is equal to 3. So it means n is going to run while n is less than 3. So it's pretty much going to run 3 times. It's going to run from 0, 1, and 2. Now, I'm going to come back to this in a second. I just want to look at the second loop. Now, the second loop, what it does, so what we basically do is iterate 3 times. And then what we do is each time we loop in the outer loop, we're looping through the numbers to check for a smallest element in the list. So find the minimum element in the unsorted part of the vector. Now let's look at how many times j will run. Now j is equal to I plus 1. So j starts from 1, like 1 more than I, but it ends at n, less than n. So here is the difference, is it will still run 3 times. So it will run, let's just say I is equal to 0. So j is going to run, and when I is equal to 0, j is going to run from 1, 2 to 3. So 1, 2, 3, so 3 times. But when I is equal to 2, j is only going to run twice. And when I is equal to, when I is equal to 0, j is going to run 3 times. When I is equal to 1, j is going to run twice. And when I is equal to 2, j is going to run only once. So basically what's happening is the following. Let me just copy that comment and bring it down here. So I is going to run 0, 1, 2 times. Or we can call them iterations if you like as well. Okay, I'll just say times. While j is going to run n minus 1 minus I times for each iteration of the outer loop, which is I basically. Okay, so let's have a look at what happens in the first iteration. So I'm going to have another comment like so. And let's see what our vector looks like at this point. Okay, so in iteration 1, when I is equal to 0, when I is 0, the sorted part of the array is empty. The unsorted part is 5291. So pretty much the same as what we started off with. Okay, now what we want to do is we want to assume that the current index is at the minimum. So minimum index is equal to I, which is pretty much 0. So what we are assuming, the minimum index is equal to I, which is 0, which holds element 5. So if we scroll slightly up, this is index 0, which holds element 5. Okay, so here we want to assume, to start with, that the minimum value of the list is 5. It's not really 5. But now what we're doing is we're going to check all of these items and see what is smaller than that value. And if there is, we do a swap. So that's what's going to happen in the second loop. And the reason why I said we're only checking this part is because j is going to be equal to I plus 1. So it's going to start from here. It's going to compare with this value. So at this point, we can say that I is equal to 0 and j is going to be equal to 1. Well, j is not defined here yet, but I just want to keep everything in the same place in the comments. So what's really happening here is we are saying that if this value, so if this value is smaller than this value, replace the minimum index to be j, which is 1. And then when j becomes, say, 2, we are trying to compare this value with that minimum value. And when j becomes 3, we are comparing this value with the value that's sitting at the minimum index, which was the last, which was number 2. So we're basically, what we're doing in this whole process is finding the smallest value in the unsorted part of the vector. Okay, so that's the unsorted part of the vector, but we are checking these items. And so we're checking if there's anything smaller than what we started off with, which was 5, and just kept on updating that value. So let me just show you how this works. So I'll bring this back. I'll just put it here. It makes my life easier. I'll do it slow-mo for the first iteration. So basically here, let me just bring this down slightly. Yeah. So what we're basically saying here is if whatever value is, oh, I'll just do it. Whatever's sitting at j, so j is 1, so that's 2. If 2 is less than whatever's at minimum index, which was 0, 5. If it's true, then in that case, we update the minimum index. The minimum index was 0 at that point, but now it becomes j, and then minimum index is where j is equal to 1. So that's, then now we found there's a smaller value than 5, which was 2. Next, we increment j. Now j becomes, let's do it like this. J is equal to 2 now. And then now what we do is we check whatever's sitting at j, which is 9. If 9 is less than whatever's at the minimum index, which is now 1, which is 2. So is 9 less than 2? No, it's not. So this part doesn't happen. Then j becomes 3. Now, if the value that's at minimum at index 3, which is 1, is less than the minimum index, the value that's sitting at the minimum index, which is 2. If this is true, then we do a swap. So that's actually true. So the minimum index is 3. So now we've finished from this loop. So when we complete the loop, the minimum element is the value is 1 at index 3. So then we keep going. Now we've finished. So now what we want to do is we want to swap the current element with the minimum element if they are not the same. So if minimum index, which was, we started off with, sorry, the minimum index was 3. If 3 is not equal to I is still 0. So at this point, we're still working with I being 0. Okay, so I think I scrolled too much. So this is actually true. So we go down and do the swap, which pretty much says, let me bring the original list. So we swap whatever is a I, which is 1, with whatever. So we swap basically 1 with 5. Something like that. So the list pretty much looks like 1, 2, 9, 5. And for debugging purposes, we can actually print out our list just to see what it looks like after each iteration. After each iteration. I might want to put a new line right here and right here. I think it's called array. Yep, I guess that should be it. Okay, so that's what's pretty much happening. So at this point, I've got some work that I mentioned here. At this point, what we basically did is we swapped the minimum element with the first element. So vector after swap is 1, 2, 9, 5. The unsorted part is now 1. Sorry, the sorted part is now 1, so we don't play with this anymore. And the unsorted part is 295. So we'll be working with just this part. But in the end, we are basically working on the same lists, but officially we've sorted out the first elements. So let's look at our first iteration. So an iteration after each iteration. So this is what it looks like, 1, 2, 9, 5. So it's pretty much what we said it will be. Okay, let's go to iteration 2. Let's see what's happening at iteration 2. So iteration 2, when I is equal to 1. Okay, so now we are here. At this point, the unsorted part of the array is actually, the sorted part is 1, and the unsorted is 291. Now the minimum index is going to be 1 because the minimum index is equal to I, and I is 1. I is 1. Okay, which holds element 2. So that's index 1, which holds element 2. Okay. All right. And J resets, J is going to be equal to 2 because now I plus 2. So we start off with J equal to 2. So that's what's happening. Now the process repeats. So I'm just going to erase whatever's here because now it's just a new set. But what we're basically doing is we are comparing this value. If we're trying to find, so this list has changed actually. I should bring it back here. That's what it looks like. So that was the original list. Okay. This is the list after iteration 1. So basically what we're trying to do is we're trying to see if there's a smaller value than this, but there isn't. Okay. So up to this point, let me just, so the minimum element remains at index 1. I'm just trying to bring out some, there's no need to do a swap. So here, the minimum element is 2 at index 1. Why did we say 2 at index 1? Because the minimum index is 1, which has the value 2. So basically we're saying if the minimum index, which was 1, is not equal to 1. So this is false. So in that case, that's now no swap happens. Okay. So we can say there is no need to swap since the minimum element is already in the correct position. So here the vector remains as 1, 2, 9, 5. The sorted part is now 1, 2, and the unsorted part is 9, 5. So the vector will still print like this. I'm just going to run and show you what it looks like after the second iteration. So pretty much this condition doesn't happen. So after iteration 2, it's still 1, 2, 9, 5. I think the way this thing is printing is not very nice. Okay, all right, let's go to iteration number 3. So this should be our last iteration because we did say that I is gonna run 3 times. So iteration 3 when I is equal to 2. Okay, now the unsorted part is, sorry, the sorted part is 1, 2. The unsorted part is, so that should, because that should have changed to 9, 5. Sorry, so previously this should have been like this, but I forgot to update it, so apologies for that. So it's now looking like this. So the 2 goes up. Now this is already sorted. We won't touch it anymore. The minimum index is equal to I. and I is equal to 2. So the minimum index is equal to 2, which holds element 9, because that's index 2, that holds element 9. And at this point, I is equal to 2, j is equal to I plus 1, which means it's going to be equal to 3 when we come down here. So I is going to be 3. So pretty much the last iteration is going to run only one time for j, okay? All right, so after the second loop, so this is it, this is what we had. Now, so basically what's happening here is we're checking if this value, which is 5, if 5 is smaller than whatever's sitting at index I, which is 9, which is true. So here a swap happens, okay? So a swap happens, so the minimum index becomes j, which is 3. So here the minimum element is 5 at index 3. So index 3, the element is 5. And here a swap actually happens. We swap the minimum element with the first element of the unsorted list. So this changes. So if 3 is not equal to I, which is 2, this is true. So we come here and we actually do a swap. So now that's what the list looks like. So at index I, we do a swap with, so that's index I, which is 2. We swap with the minimum index, which is 3. So these two swap with each other. That's what happens. And I should put it in a comment. Okay. Now at this point, I'm just going to change my comment here with this line. Swap the minimum element with the first element of the unsorted part. Vector after swap is 1, 2, 5, 9. And the sorted part is 1, 2, 5. And the unsorted part is 5. Let's run it and see what this looks like. Compile and run. And I have a problem here. Got to comment. I mixed C++ with normal language. It's not happy with it. So after the first, I kind of fixed the way this looks like. After each iteration, it looks better. Now we can see this is 1, 2, 5, 9. Which brings us to the final vector, which is the sorted vector 1, 2, 5, 9. So in reality, we really want to get rid of all these debugging messages, but I've kept it here for explaining purposes. So what do we have to say about this? Oh, I did say that I'm going to talk about the last part somewhere here, except the last one, which is already sorted. So I'm going to put this in a comment to explain why. And then I'll read my comments out loud. Just give me a second while I fix my comments. Now, the reason why we don't check the last element is because the last element automatically falls into place because all the other elements are already sorted. This is why the selection sort algorithm typically runs for n-1 iterations. Now, we did want to say why it is in the order of n squared, or why it's a quadratic time in complexity. I've written some words about this somewhere, I think, here. So let's go down and read. The time complexity for the selection sort is in the order of n squared, both or all in the cases of best average and the worst case scenarios, where n is the number of elements in the array. This is because it involves nested loops, one for iterating through the array. So that's the iteration, 1, 2, 3 in our case, for finding, and then another one for finding the minimum element in the unsorted part of the array. So the first loop was for the iterations. So this is going to run, so I is going to run n-1 times. And the second loop is for j is just there to find the minimum element in the vector, while j not always will run. So like in this case, it ran three times the first time, and the second time it ran twice, and the third one once. But it doesn't matter. The dominating complexity here is n by n. We're not looking at the the small differences there. So I like to sum it up with this line. Think of it as having to do something n times, and for each time you do it, you have to do it another n tasks. Even if that n tasks is slightly less each time, still it's counted as n tasks because the dominating number of times is n, if that makes sense. So this results in n times n tasks. So n times n is n squared. That's pretty much it. I hope this really helped simplify, or at least sort of dig deep into how selection sort works, and help you understand why it is n squared in all the cases, because we've got nested loops, basically, one inside the other. Yeah, so I hope this helps you, and I'll see you in the next one. Thank you.